The host. Okay, we can start now. Now, so we're looking at the final topic before we look at the real zero knowledge groups. So we're looking at the rank 1 constraint system. So through our course, as we do the rank 1 constraint system, we learn how to write the zero knowledge proofs. Okay, the content we get to learn here will be very much related to what we'll be writing when we begin the zero knowledge proofs. So they're very much related. So it's very important. Last time we were looking at the algebraic circuits. So now we use the knowledge of the algebraic circuits. We take the algebraic circuits and convert them straight away to rank 1 constraints. So we just convert them. So we learned how to write the algebraic circuits. That is the knowledge we'll be using in our lesson from today hence. Because once we know how to write the circuits, the algebraic circuits, we just convert those ones to rank 1 constraints. And then once we know how to tackle the rank 1 constraints, we'll be now ready to begin tackling the zero knowledge proofs. So that is the only thing I wanted us to note before we proceed. So I've said that this lecture would then cover, or throughout this lecture, we'll be learning how to transform the algebraic circuits into rank 1 constraint systems. Now, so briefly, what is a rank 1 constraint system? What is it? So what shall we be looking at? Now, so you're given an equation, and this equation, supposing it has only one multiplication, equality, and the other side, the other side. Now, once there is only one multiplication, the additions could be several. The additions could be several, 1, 2, 3, or several. But multiplication, the equation should have only one place of multiplication. So where there exists more than one multiplication, we'll be maneuvering around to ensure that we only have one multiplication in the whole equation. So that is what we'll be doing. So we'll be taking the arithmetic circuits. After writing the arithmetic circuits, we try to convert them to rank 1. So how are we converting? By just ensuring that where there exists several multiplication, we make it 1. So there'll be a way of maneuvering. So that is why it's important from the very start, we become very keen with whatever we'll be doing. Now, so this knowledge I've said will be important in writing zero knowledge proofs. And of course, I've also noted here that it aligns with the bilinear pairings, which we did earlier. And because of that, it will also be aligning with what we require in the ZK snacks or the snacks. Now, we recall this bilinear pairing, where these are the inputs, these are the groups, the pairing groups, and this is the target group. Now, we will not go back to this, but we're just saying that the knowledge of rank 1 constraint systems will align very well with the bilinear pairings that we already did. And so that will be very important to us. And again, it will be aligning with the ZK snacks. That is what we'll be looking at when we begin the zero knowledge proofs. Now, just straight away, let's go into how do we convert the algebraic circuits into the rank 1 constraint systems. Now, I've used this one interchangeably. I've used one. You get familiar to this. So in some places, I've just used the word one. In some places, I've used this one, and they mean the same. But I needed to be consistent. I would have chosen on one. But both of them are used in literature. Both of them are used, so there's no problem. So, what was a witness in our arithmetic circuit? What was our witness? Let me just give an equation, for instance. Supposing somebody says that x2 plus x1 is 8. Now, what is our witness in our case? In this case, our witness would be the value of x2 and the value of x1. That's what we shall call a witness in as far as rank 1 circuits are concerned. But now, when we come to this was the witness. X2 and X1 are witnesses as far as the arithmetic circuit is concerned. But when we come to rank 1 constraint, we need to know what a witness is. This could be part of witness, but they are not the only witnesses. X2 and X1 are not the only witnesses. So then we'll get to know, once we come across an arithmetic circuit with our agenda would be, first of all, identify a witness in that arithmetic circuit. How many witnesses do you have? And that's what we'll be doing. So I've just given this a simple example. In this simple example, in terms of arithmetic circuits, we've seen two witnesses, X2 and X1. But now what happens as we proceed with the rank 1 constraints? So it's important for us to get to know what our witness is as we proceed. So I've said in the rank 1 constraints, the witness vector will be a 1 by n vector, 1 by n. This is what I mean here by 1 by 1, it means it has one row and n columns. One row, so the first number stands for the rows, number of rows, and then number of columns. So we are saying that our witness will be a vector that has one row and n columns, and it will be containing values for all inputs. Values for all inputs. In our case above, we've seen x2 plus x1 was equal to something 8. So the inputs here will be x2 and x3, x1. In terms of the arithmetic circuit, this, and I've said they will not be the only inputs. They will not be the only inputs in terms of the rank 1 constraint. So that it means that we need to know what are the other inputs in this. But then let's just define again what a witness is, and then we proceed with examples to get to know what a witness is. Now, so I've said in terms of rank 1 constraint system, a witness will be a vector with one row and n columns of all the input variables, all the inputs. Now, the other witness will also be the outputs. So in cases of the rank 1, we mentioned x2 and x1, but we're also saying that in terms of rank 1, the outputs will also be witnesses, will also form witnesses. And the other witnesses will be formed by the intermediate values. Remember, I said that where there are several multiplications, we'll be ensuring that we only have one multiplication. So we'll be dealing with those several multiplications to ensure that the end result only has one multiplication, so that we only have A times B is equal to X. So that means we had several multiplications. For us to end up with one multiplication, we have other intermediate values we have other intermediate things we'll be doing. And so as we do those intermediate procedures, we come up with the intermediate values, and those intermediate values also become witnesses. So the witnesses here, one is the set of the inputs, x1 and x2 in our case, and then the output variables will also form a witness, and then we have the intermediate values. And all these values, all these witnesses I've mentioned, we are writing them in form of a vector, one row in one row, and then several columns, n of them, n columns. So these n columns would depend on how many input variables do you have, how many output variables do you have, and how many intermediate values do you have. So those are what will be making the columns. Those will be our columns. But then we write all of them in a straight line, that is one row. So that is how we'll be writing a witness going forward, even as we move towards the zero knowledge proofs. Now, so we now know what a witness is. Of course, we'll be looking at examples, and the examples will assist us to know what I mean by input variables, what I mean by the output variables, and what I mean by the intermediate values. Now, I've also noted here that by convention, the first element of the witness will be one. The first element of the witness will be one. So what that means, before you list the input variables and the output variables and the intermediate variables, you first have to mention one. So that means your vector would have one as the first entry of the witness. And then after that, you will then list the output variables and the input variables, and then the intermediate values. So one, you must remember one has to come as the first element of that witness. Why is that necessary? I've given a reason. I've said that this would then be so as to simplify calculations and allow efficient constraint representation. And we will see this in our example. So the main idea is we have to include this one just to simplify our calculations, and also to ensure that we allow for efficient constraint representation. Constraint, I know you know, these are just the equations. These are the equations. So we need to come up with a better way of representing these equations. Now let's look at this. Let's look at this arithmetic circuit, and we want to convert this to rank 1 constraint system. So that means we must first, we have to come up with the constraints, then come up with a witness, and so on. That's what I want us to do. That's what I want us to do. Now, when you look at the right-hand side, you discover that we have several multiplication. This is just not one multiplication. We have x multiplied by x to give us x squared, and the result is multiplied by y. So these are several multiplications. And as I said, in rank 1, we require only one multiplication on this side. This side, we have no problem. We only have one value here, there's no problem. But our problem is where we have several multiplications. If it were just one multiplication, we would have no problem. So what we then do is we want to ensure that we have one multiplication. And so that is now where our intermediate variables come in. That is where intermediate variables come in. So the first thing I would do, the x times x, I would call it V1. X times x, I call it V1. And so, therefore, our Z becomes V1 times Y. So you now realize that we have only one multiplication on the right side, and that is what we wanted. So every time we have several multiplications, we will maneuver around to ensure that we have only one multiplication, as we've just done in this case. And in this case, we had a very simple thing. And so it will be very interesting how we maneuver around it when it becomes complicated. But for our case here, it's very simple, just to assist us understand what we'll be doing. Now, this was our Z. This was our Z. And it was x squared times x times x times y, x squared times that. Those are several multiplications. So I just decided to take this. That is not, it's not must, it must be that way. You can even come up with another way. You can even say that this is the same as, Z is the same as x times y. And so that you see, you can even say that V1 is xy. And then say that Z, therefore, is x times V1. If you want, you can do that. But now, we have to look for the easiest way of doing it, the easiest way. But this is another way you would have done it if you wanted. So long as you're getting one multiplication on one side. We have no problem with the addition. If there were several, there would be no problem. If there were 2, if there were 5, addition, and so on, we would have no problem. But once the multiplications are more than 1, we have a problem there, and therefore we have to ensure that we only remain with 1. Now, interesting is that we now have 2 constraints, 1, 2. Remember, we talked of the witness being a vector, 1 column, 1 row, and several columns. We had a witness, 1 row, and several columns. So let's just identify how many inputs. Now, what are our witnesses here? What are our witnesses here? So supposing somebody was to tell us that this person knows Z. Supposing this person is telling us he knows Z, and we want this guy to prove that he knows Z. So what are we expecting this person to give us? So we are expecting this person to give us X, to give us Y, to give us Z. If you look at this, so that he's telling us that if X is 3, if I take X to be 3 and Y to be 2, then X squared will be 9 times 2, that is 18. So he's telling me that Z will be 18. So he's telling me that X is 3 and Y is 2 and Z is 18. So these are witnesses. These are witnesses. So whenever he gives me X and Y, he must give me Z. We are saying that this person wants this thing to be not to be known. He doesn't want to reveal what Z is. He knows Z, but he doesn't want to reveal what Z is. So I ask him, show me you know Z. Then he gives me Z. He gives me 18 as Z value. Then he gives me X as 3, and he gives me Y as 2. So it's just me to go through this and see whether it's correct. So if I was to ask him again to show me, Z, another round, he would again now tell me that at this time assume X to be 4 and Y to be 3. And so this will be 16 times 3. And so he tells me that X is 48. Is it 48, 16 times 3? Yes, 48. So every time you ask him to show that he knows Z, he gives you witnesses. He gives you a value of X, he gives you the value of Y, he gives you the value of Z. But now we are saying as far as rank 1 constraints is concerned, these are not the only witnesses. It's not only X, Y, and Z. While we were doing that, we came across an intermediate value, V1. So it also becomes a part of this witness. And we also say that the first part of that, the first entry of that vector should be 1. So we now have our witness as this. This is our witness. This is now our witness 1, what we said we must always enter as the first entry, then Z, then X, then Y. After you've listed the entries, you can now list the intermediate values. Intermediate values. So our intermediate value was V1. So this person, therefore, the witness, this is the witness now. This is now the witness. Thus, the witness vector is this. Now, when we talk about witness, this is what we'll be referring to. If you're given an equation like the one we have above, and you're asked for witness, this is what we are asking for. So that if I was to ask this guy to prove to me, to show me that he knows what Z is, I expect this person to give me these values. I expect this person to give me Z, X, Y, and V1. And the other time I ask for the same again, the other time I ask for this person again to prove he knows X, Y, he knows Z, again, he gives me these witnesses. He gives me all this. Now, so we say that a witness is just a vector made of one row and several columns. You can see in our case, the columns are 1, 2, 3, 4, 5. These are 5 columns in our case for this very easy equation. Now, so I've just given an example here to just illustrate what I mean by a witness. So I asked this guy to show me he knows what Z is, and this person he then tells me X will be 3, Y will be 2, Z will be 18. Then he tells me what V1 will be, and so it's now upon me just to go through the calculations and see whether what he has given me makes sense. Go through the calculations. So every time you ask him again, he gives you other values. So they are just generated randomly generates values and then gives you those values. So that means if this is what this guy has given me, then it means the witness is this. Because he has told me what there's a 1, then there's a Z, there's an X, there's a Y, then there's this intermediate value, V1. So this now becomes a witness. Now, if you ask him again, he randomly generates the other values and gives you these other values. And again, as witness. Now, once again, I've just emphasized why the 1 is there. I've said the extra 1 term is included for convenience. Is included for convenience. And of course, as we proceed with the several other examples, we'll see how it must be added there. Now, so I've just used an example. This is just a simple example of how to transform. Of course, we've seen the above example. But let's look at this other example. This other example is very easy because we already have only one single multiplication. Only one single multiplication. So there's not a lot to be done here. There's not a lot to be done here because there's nothing we are converting on in terms of multiplication, because we already have one single multiplication. If there were several multiplications, we would have worked out just the way we did for the previous one. But in this case, we only have one, and so it's needless to convert this. Now, so important is now, what is our witness at this point? What is our witness? Because we have no intermediate values. So our witness, as I've said, would be the value 1, then Z, then the entry points, the inputs, X and Y. If there was an intermediate value, we would then have mentioned it here, but there is none. In this case, there is none. This is not like the example we saw above. That one had intermediate values. So that means if I was to ask for this guy to give me witness, to show me that he knows what these values are, without telling me the exact values, this guy can randomly generate and give me, for instance, can tell me that X is 41 and Y is 103, so that Z becomes that. And so the witness therefore becomes 1, and then the Z, 42, 23. Then after that, the entry values 41, then 103 becomes the witness. So this becomes the witness for this. Now, so what is also important is how do you write Rust that will then be either generating these values if you want, or if you don't want to generate values, Rust that will then be just confirming that the inputs, the witness that he has been given, the witness you've been given are correct. So that is what is therefore interesting. We'll be looking at that in a short while. Now, just before that, again, let's just mention something. There's something I've written here. I've said before constructing a rank 1 constraint system, you must ensure that it follows the following form. So we have the result, then we have the left-hand side, and then the right-hand side. The result, the left-hand side, and then the right-hand side. That every time we are writing rank 1 constraint systems, we ensure that that order is followed. Like in this case, the one that we've just been looking at, you can see the result, the left-hand side, and then the right-hand side. So every time you're doing that, you must know what the left-hand side is and what the right-hand side is. When I talk of the left-hand side, I don't mean something on the left, this side. I just mean this side where we have multiplications, where you have multiplications. Which one is on the left and which one is on the right? This other one is just the result. This other one is the result. So every time you are writing a rank 1 constraint system, it must follow that order. It must follow that order that we have the left side and the right-hand side. So of course, I was just emphasizing the same thing here. That this is the result, the left-hand side, and this is the right-hand side. Now let's now look at maybe more advanced equations. But not very advanced because you have to go step by step so that we get to learn what is happening. Now, our first example, we looked at several multiplications, and again, maybe we again revisit using a different example this time. Using a different example this time around. Now, what is the goal? What is our goal? Our goal is to construct a system of equations of this form. A system of equations of this form, where we have the result multiplied by the witness. Multiplied by the witness is equals to the left-hand side multiplied by the witness, then multiplication multiplied by the right-hand side multiplied by the witness. So that is our goal. Every time we have an equation, arithmetic circuit. Every time we have an arithmetic circuit, we want to ensure that we write it in this form. Every time we have it, we must write in this form. So this is our goal, and we want to move slowly and see how to arrive at that. Now, we'll be converting all these things into vector form, into matrices, of course, and then we just multiply. This is a vector. This A is a vector. We already say that this vector is one row and several columns. So like we can have, in our previous example, we have had Z1, Z, X, and Y. So this is a vector. So in most cases, we'll be writing it in column form. Writing it in column form so that we can multiply it by matrices on the left side. So writing it in most cases, we'll be writing it in column form as we proceed, just for easier multiplication. Now, so how do we then construct our matrix for the left-hand side, and then matrix for the right-hand side, and then the matrix for the result? And so that is what we then look at. Of course, A, we've already known how to come up with the A. Our A is our witness. Our A is our witness. But again, we'll be writing it in column form. Just the same way I've shown before. Writing it in column form. But now, most interesting, how do we come up with the left-hand side matrix? So that is what I want to explain, and also how to come up with the right-hand side. Now, let's consider this example. And from this example, and also consider the equation we had. The equation we had was Z is equals to X times Y. Now, I want to consider this witness, and at the same time consider this. But before that, how many columns do we see? 1, 2, 3, 4. It has 4 columns because of the elements we entered. Our witness has 4 elements. And so because of that, we would have 4 columns. Now, remember our point is to construct this matrix. So this matrix is supposed to have 4 columns. It's supposed to have 4 columns. Now, how many rows will this matrix have? The number of rows that this matrix would have would be equivalent to the number of constraints we have, the number of equations we have. In our case, we only have one equation. So if we have one equation, it means this matrix would have 1 row. And since the witness has 4 elements, this matrix would have 4 columns. Supposing we had 2 equations, this matrix, and even this, would have 2 rows. So if you have 2 equations, you'd have 2 rows. If you have 3 equations, you'd have 3 rows. If you have 4 equations, you'd have 4 rows for each of these matrices. And the columns would depend on this the witness. So each of these matrices would have 4 columns. Of course, they're not the same matrices. So therefore, how do we come up with the L? But we've already known the basics. We've already known that each of these matrices would have, its number of rows would depend on how many equations you have. So if you have 1 equation, then you will be having 1 row. If you have 2 equations, you'll be having 2 rows. You have 3 equations, you'll be having 3 rows, and so on. And the number of columns of each of these matrices would depend on the entries or the elements in your witness. So if your witness has 4 entries, as this case, then we would have 4 columns. But if the witness has 5 entries, you would have 5 columns, and so on. So those are the basics. So let's now go to, let's now form our matrix. Let's now form our matrix L1. L. A matrix L will be, remember the witness. Let me just write the witness here. 1, Z, X, Y. Now, our equation was Z is X multiplied by Y. The left side is X, and you are forming the left matrix. So what that means, that the entries on the left side, while you are forming this matrix, while you are forming the matrix L, the entry on the left side is made 1. So where there is X, I make it 1. The entry on the left side is made 1. And the other entries are converted to 0. The other entries are converted to 0. So that is why you see this matrix. This is a matrix L. Now, what about R? Again, I just write our witness, 1, Z, just to make it simple so that we understand what is happening. R is the right side matrix, the right side matrix. The entry on the right side is Y. That is the entry on the right side is Y. So I make that entry 1, and the other entries, I make them zeros. The other entries, I make them zeros. And that is why you see this matrix, and I've called it our R. This matrix, I've called it our R. Now, what about the result? Again, this matrix, I'll call it the output. Call it the output O. The output O. Again, I just write, the witness 1, Z, X, and Y. And our output was Z. So Z, I make it 1, and the rest, I make them zeros. The rest, I make them zeros. And so you can see X 0, 1, 0, 0. And this matrix, I've called the output. Now, A. We know what A is. Our A is this, the witness. Our A is the witness. And so this is our goal. This is our goal. Every time we have an arithmetic circuit or an equation, then we want to write it in this form. We want to write this equation in this form. Once you write it in this form, then you are now in a position to write a Rust code that would then be verifying whether the witness is correct. Whether the witness is correct. So if you can write it in this form, because this is what we'll be writing, when you are writing our Rust code, this is what we'll be using. This is what we'll be using. You'll see an example of the Rust code just in a short while. Now, in our example above, this example, we had said that is supposing Supposing this guy, let's just go back. Our example here. This is the example I'm using. So I'm just using this example to show how our matrices will be working. This is what we are looking at. This is what we are looking at. Our Z in this case is that, our X and our Y. And so this is our A, our witness. This is our witness, A, then that, then that. And then we've come up with the L, we've come up with the R, and we've come up with the O, the output. Let us see that they are correct. Let's just see that they are correct. And that is what Rust code will be confirmed. Let us see that they are correct. So we've come up with, this is our output. This is our output, and this is our A. So how do we normally multiply matrices? It's a row and a column. So this element, as you add the results, that's how we normally multiply. So it's 0 times 1, the result plus 1 times 4323, then plus the result 0 times 41, then plus 0 times 103. So you can see that this will be 0, this will be 0, this will be 0, but this will be 4223. 4320. So you can see the one we put here, how it's making our calculation conveniently, how it's helping us to do our calculation conveniently, our calculations. So you cannot avoid to put it there. You must put it there, because if you don't put it there, then you'll be having more columns here than the rows. You see 1, 2, 3, 4 columns. So the rows must also be 4. So that is why we said you must always include 1 in your witness. And I said going forward, we'll be seeing how this one is important. So avoiding it makes our calculations impossible. We can never calculate, we can never multiply these matrices without this one. So the left-hand side has given us 4223. When you multiply this plus this product, plus this product, plus this product, we've gotten 4223. Now let's do the right side. It's this product, plus this product, plus this product, then plus this product. Now this product is 0. This product is 0, and this product is 41. This other product is 0. Then there is multiplication there. There's multiplication, this multiplication. Is there multiplication? Again, let's do this product. This was our R. Remember, this was our L, and this was our output. And this was our A, small a, small a, small a. Let's do this product is 0. This product is 0. This product is 0. And this product is 103. So you can see it's true that the right-hand side, the product of the right-hand side gives us what we have as the output. So that is what we'll be doing with the Rust. So Rust will be confirming this, so that you confirm that the calculations are correct. But we'll be looking at more complicated examples than this one going forward. I've already explained this. I already explained why there's a 1 here and a 0 elsewhere. Remember, this was the 1. When you're writing the witness, this was our 1, this was our Z, this was our X, and this was our Y. So at the left matrix, X becomes 1, and the rest go to 0. And then again 1, Z, X, Y, the right matrix, y becomes 1 and the rest go to 0. And then 1, z, x, and y. And then the output was z, so z becomes 1, the rest go to 0. So that's how we do it for this simple example. But going forward, again, we'll be looking at complicated ones, and it'll be very interesting how you come up with the left matrix and the right matrix and then the output matrix. Now, so the Rust code to verify this calculation is this. I'm using ND array. This is just to come up with the matrices. These are arrays. And then we have the main function. The main function, I define the matrices. The output 0, 1, 0, 1. No, 0, 1, 0, 0. And then the left matrix is 0, 0, 1, 0. And then the right matrix is 0, 0, 0, 1, what we had. And then I give it the witness vector. The witness vector, our A, in our example was this. And then after that, we tell our Rust now to compute the left and the right side of equation. Compute the left and the right side of the equation. The left side of the equation is the output matrix times the vector. The output times the vector. And then the right side of the equation, remember the equation was this, xy. But we're not using that, we are using this and that. So it was supposed to be OA is equals to LA multiplied by LA. So this is what we are computing at this point. So let the right be LA multiplied by RA. R has been defined, L has been defined, O has been defined, A has been defined. The matrix will be able, this code will be able to do that. And if it finds that the left side equals the right side, then it's supposed to tell us that the result contains an inequality, and therefore the RICS constraint, the rank 1 constraint system, is verified successfully. But if it finds that the left side does not equal to the right side, then it must tell us that this is not successfully satisfied, is not verified. It's not verified. So every time you do any problem, you cause in cases of in the event of coming up with this left matrix and right matrix and the output, in the event of coming up with this, if you mess, then this code will tell you that your computation is not verified. Now let me just share that code and we'll see how it works. Okay, this is the code. I don't know whether you can see the cargo tow mill.
Yes.
Yes, so because of the ND array, you have that, and then of course you're using it. using that. So then you define the outer matrix, the output, then the left side matrix and the right side matrix. Then you input your witness here as an array. And then you are telling it, find the left side. The left side will be, of course, OA, output times A. Then find the right side, which will then be the left matrix times A multiplied by the right matrix times A. Then let's run it. So if you run it, it tells you that the rank 1 constraint has been verified successfully. That just means that your calculations for these matrices were correct. Because if you make it wrong, for instance, let me just change this left matrix. Just change one entry here. Let me put here, for instance, 0 and put a 1 here and see whether it will accept. Let's just do that and see whether it will accept that. Okay, so it did not accept it. It says the result contains an inequality, and therefore, but there's an error here. Process didn't exit successfully. It didn't exit successfully. That means the left side, although we have an inequality, which the inequality, we have the equal sign, but the left side and the right side is not equal. The left side and the right side is not equal. So if we return the way it was, let's again see what it tells us. Okay. So it says they're equal. So it's verified successfully. It's verified. So that means our problem is this computation of this matrix. Once we compute them, and then of course, once you come up with the right witness, let's put in a wrong witness. Let's put in a wrong witness. Let's put here 42, so that somebody claimed to know Z. Somebody claimed to know Z, and we ask for him to prove, and he has given us a wrong value of X. He has given us 42. Let's see what happens. Again, it does not accept because the witness given is not correct. It's just saying that this product, these 42 times 103 can never give us the Z this person has given us. So every time giving a witness, you must give the value of X, give the value of Y, give the value of Z, and if you have intermediate values, again, also put those intermediate values. Now, but this was for a very simple example, and as we go forward again, we'll be seeing how to do that. And of course, the only thing that will be changing is how to calculate O, L, and R, but how to come up with the witness is not. Okay, of course, again, it will be changing depending on how many multiplications do you have. And as I said from the beginning, if you have several multiplications, you have to reduce them, as we saw in our first example, that you make them one. You make it one multiplication at every step. So let's continue. Now, for this question, I have a simple question here, and of course, I've answered it. I've said, why use rank 1 constraint systems instead of simple equations? Now, so the question is, in this example, why use the rank 1 constraint system? Now, so the thing is, somebody will be asking that question, but I've said that this was a very simple example. So being a simple example, one may think that a rank 1 constraint system will not be important for you to prove that you know Z, for you to prove that you know Z, which is XY. But we are saying that we have complicated examples I will be doing. Now, again, the thing is, it's not rank 1 constraint system. We've already said how important it is. And that is why, of course, we are using it. Although the example we looked at would have been done with that, but of course, we are saying that we need rank 1 constraint system in terms of proving the efficiency in zero knowledge proofs, zero knowledge sanctive non-interactive arguments of knowledge, which is the ZK snacks. So we shall be seeing how these rank 1 constraint systems are then implemented in ZK snacks. That is in our next topic. So that is why it's important to understand it. Now let's look at something a bit complicated. Let's look at something a bit complicated. Now we can see several multiplications on the right side. This is what we have. What we have is R is X, Y, Z, U. X has been multiplied by Y, has been multiplied by Z, and then, so these are several multiplications. These are several multiplications here. So as we've said, whenever we have several multiplications, we make it 1. So one way is maybe to call this one V1, call this one V1 as XY. Then once you have V1, that one as V1, you can call this one as V2. You can call V2 to be Z times U, so that we now say that R is V1 times V2. So now we have only one multiplication. We have only one multiplication. So this is one way. Okay, let me just again write it. Let me just again write it. Let me write it properly. Because the thing is, what is our witness? That's the thing. So supposing this person claims to know Z, to know R, what are the witnesses? What are you expecting this person to give to us? What are you expecting this person to give to us? So we have R is X times Y times Z times U. We're expecting this person to give us V1, XY. So this person to give us V2, ZU. So what is our witness? Our witness, therefore, our witness would be 1. We said we have 1. And then we would have our output. Our output. Then X, Y, Z. X, Y, Z, U. Then after that, we have our intermediate values, V1, intermediate value V2, in that order. This becomes our witness. Our witness has how many columns? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 columns. It's very interesting that we now need, from here, we have to come up with the L, the leftmost. The leftmost, oh, okay, the left. Now you check, you look at this, and then you want to, okay, we'll not be using this, we'll be using this. How many rows do you have? How many rows do you have? The rows that we have, 1, 2, just ignore this because this one has been rewritten as R is V1 times V2. So we now have 3 rows. We now have 3 rows. The first row is the first intermediate value V1, which is X times Y, then V2, which is Z times U, then R now, which has now been written as V1 times V2. So we have 3 rows. So our L must have 3 rows. You begin the first row. Begin the first row. The first row is this. The first row is this. The leftmost is X. So the first row is 1, R, X. I'm just doing this so that I tell you what we do after that. U, V1, V2. But the first row has the leftmost as X. X is the one on the left. So X is the one that goes to 1. X is the one that goes to 1, and the rest goes to 0. The rest are zeros. X is 1. So you can see how easily it is to come up with a L. Now you go to the second row. Second row, the one on the left is Z. The one on the left is Z. So again, you just write. But where the Z is, you make it 1. So the rest is 0, 0, 0. Then Y will be 0. Then Z will be 1. Then this will be 0. Then 0, and then 0. Then you go to the third row. Again, the one on the left is V1. The one on the left is V1. So the rest is 0. So V1 will be 0. No, will be 1. The rest will be zeros. V1 is the last one here. Is 1, and the rest. So this is our left matrix L. This is our matrix L. Then you would come up with the matrix R, again using the same order. Now that time, you'd be considering the one on the left for every row, the one on the right, the one on the right for every row, and so on. Now, this is not the one I did. This is not the, okay, this is one way. This is one way of coming up with the constraints. It's not the only way. It's not the only way of coming up with the constraints, but it's one of the ways. Is there another way? Let's check and see whether there's another way. But our goal is to ensure that R is written on the right side. We only have one multiplication. So there are several ways you can achieve that. We've seen one of the ways of achieving that, that we combined these two, then combined these two. So we call this one V1, call this one V2, and then that then means R will be V1 times V2. That is one of the ways, and is not the only way. The other way is this. I would combine, let me just again write it here. R was X, Y, Z, U. So I would decide to combine X and Y and call it V1. So that means R now becomes V1 ZU. And then I decide to call V2 as this, V2 as V1 times Z. So that now R becomes, instead of this, V2 times U. So you can see now, my final R is a product of, and there's only one multiplication here. It's a product of V2 and U. There's only one multiplication here. That is our target every time we are doing this. Every time we are doing this, you have to ensure that whatever the output you have, on the right side, we only have one multiplication. Sometimes there are additions, we have addition and subtraction. But when you have addition and subtraction, there is no limit on how many we should have. The only limit we have is the number of multiplications. It must only be one on the right, on one side. On one side. So just going through the example slowly by slowly to understand. Now, so there are these two ways, and I chose the first one. I chose to move with the first one. I chose to move with the first one. So it's this first one that I decided now to come up with the witness for the first one, and then come up with the left matrix, L, and then the right matrix, R, then the output matrix. So this is what I've done here. So I've said, let me again just write it here. Let me write it here. It was R is equals to X, Y, Z, U. And we said, let V1 be X, Y, let V2 be Z, U, so that R now becomes V1 times V2. So these are our constraints. These are our constraints. Now from these constraints, we now come up with a witness. And just before I add one, I've said, I can see there is an R. We need, this person is supposed, if this person is to claim to know R, must give us R, not the exact R, not the exact R that is hiding. Because the exact R is supposed to be secret. He's not supposed to reveal it. This guy is not supposed to reveal R, but he just gives us his R. Once he gives us his R, another one, then he must give us the X at that point, give us a Y, give us a Z, give us a U, then give us the intermediate values. And of course, the other thing he'll add us, it would be a 1. That's the other thing that it will add us, it will be a 1. So once you do that, you now have a witness. The witness, therefore, will be 1 R X, and look at the order in which they are coming. 1 comes first, then the output R follows. Then after that, we have the X, Y, Z, U. X, Y, Z, U. Then from there, you just come down, moving down. You had our V1, and then you had your V2, the intermediate values. So that then becomes our witness. Now, once you have that, again, I want to, okay, we shall come back to, I shall again rewrite it on the next page so that we now come up with our matrices, our L, but of course, at this point, you've now seen how we are getting our matrices L, R, and output. But now, just I've already erased, but what was it? What I want to again emphasize was V1 was XY, V2 was what? ZU, and then we had the R, which is V1, V2. I can see 3 equations. I can see three equations, meaning that my matrices would have three rows. That's what I've written here. I've said, given that we have three constraints, the matrices would contain three rows each. So L would have three rows, R will have three rows, and the output matrix will also have three rows. What about the columns? Again, we've already mentioned that. The witness has 8 entries. Our witness has a 1, R, and so there are 8 of them, 1, 2, 3, 4, 5, 6, 7, 8. So each of these matrices would have 3 columns. So let's now write our matrix. And again, you recall that this will be the left values, and this will be the right. So this is the left, and this is the right. And when we want the output will be, the output will be looking at R. So now our left matrix, okay, this a lot of explanations there, but we've already known what is going to happen. This is our witness. This is our witness, and we want the left matrix, our L, and let's recall what V1 was. V1 was XY. Let's recall what V2 was, ZU, and what R was, V times V2, V1 times V2. Now we go the first row. The left value is X. So X becomes 1. The rest is 0. X becomes 1. 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5. Let's go to the next row. The left value is Z. So Z will be 1. The rest will be zeros. 1, 2, 3, 4. 4 zeros. 1, 2, 3, 4. And then 1. The rest again are zeros. 1, 2, 3. And then the last row, V1 is the left, the one on the left. V1 is the one on the left, becomes 1, and the rest are zeros. The rest are zeros. This is the left matrix. What about R? We are considering the right side now. We're considering the right side. Okay, now the right side of the first row, the right side is Y. Y is here. This one becomes 1. 1, 2, 3 zeros. 1, 2, 3 zeros, then 1. 1, 2, 3 zeros, then 1. The rest are zeros. 1, 2, 3, 4 zeros. 1, 2, 3, 4. The second row, the one on the right is U. 1, 2, 3. The rest are zeros. And then lastly, the last row, the one on the right is V2. V2 is the one on the right. The rest are zeros. So this is our right matrix. Okay. Now, what about the output? Again, the same procedure. The same procedure, looking at the left side, what was the output on the left side? For the first equation, the first row, what was the output? The second row, what was the output? The right row, no, the third row, what was the output, and so on. Now, so I said these were a lot of explanations, but the thing is, all these are just explanations of what is happening. You go through it, but I've already summarized that. I've already summarized the explanations, and of course, you're seeing how I arrive at the first row, then continue the explanations, and then you see how I arrive at the second row. So just explanations, second row, and then you come finally, again explanations, and then I come the third row of our L. So a lot of explanations, you go through those explanations. It's just what I've summarized. And then, of course, I gave another alternative way is what I've just, in fact, what I was explaining was this alternative way of how to arrive at this, and it's easier. The alternative way is easier. The alternative way, of course, is you identify where of course, it is 1, the witness was 1, R, X, Y, Z, U. I think it was at X, Y, Z, U, then V1, then V2. Now, so what is V1? Our V1 was just X times Y. X times Y. So anything else that is not X and Y. So for instance, how do you write this in terms of X and Y? So it would be 0 times 1, 0 times 1, plus 0 times R, plus now X, 1 times X, because of this X. And then 0 times Y. So everything, we are just the same thing. Where there is X is where you just put 1. But the other thing just multiply by 0. Everything multiplied by 0. Then the Y, because we're supposed to have U1, V1 as X times Y. So this, everything here, this is the only one multiplied by 1. So the whole of this, we can call it X, then multiplied by Y. So when you multiply Y inside, wherever there is a 0 again, the result will just be 0. And whenever there is an X, like here, you get XY. And here you get 0, 0, and so on. So if you put, what about V2? What was V2? It was Z times U, Z times U. So where there is Z is what you put 1. Everywhere else you put 0. So 0 times 1, 0 times R, 0 times X, 0 times, but there's a Z here, multiplied by 1. Then everything else by 0, close the bracket, multiplied by U. So this is another way of looking at it. But of course, the first one that I explained, I think it was clear, and you got to understand it. Then after that, you just extract. If you're using this example, we'll then extract the coefficients and write the result in brackets. Extract the coefficients. For instance, here you extracting 0, 1, 0, 0, 0, 0, 0. And then here 0, 0. Those coefficients are the ones you then extract. Even for the right, again, we do the same. Now, I've already explained how you get R. And again, these are just explanations. Finally, you arrive at R. After all those explanations, finally, you arrive at R. What about V? Oh, let me again write just in a few minutes. Again, write that V1 was XY, I think. V2 was V2 was ZU, and then not R, this time was R, which was V1 times V2. What was our witness? Our witness was 1 R X Y Z U V1 V2. This was our witness. Now, our outputs are on the left side. Let's consider the first row. The first row, the output was V1. So where V1 is, it becomes a 1, the rest will be zeros. So you can see a 1, the rest are zeros. At the second row, the output was V2. So everything else will be 0, but V2 will be 1. So you can see V2 is 1, and everything else are zeros. And then lastly, in the last row, our output was R. So where there's R is the second one, it will be 1. It will be 1, and the rest will be zeros. So that's how you come up with the output. And then once you have the output, and you have R, and you have L, the next thing is to write the Rust code. And it's the same thing. It's the same thing. It's the same thing we wrote above. I just added something here. Ring. Just added a ring. And also just added generate, which you can also add in the last one, in the first one, generate. So that this one is just is generating values for you. Generating values for you. So if somebody asks you, prove that you know R, you can give him this person the witnesses. You can give this person R, can give him X, Y, and Z, randomly generate the values. But most importantly is that you have to say what your L is, say what your R is, and then lastly say what your O is. Say what your O is. And here, I was just asking it, generate for me X, Y, Z, and U. Of course, I know the other thing would be a 1. So I just want X, Y, Z, and U. If you want, you can ask it to generate a V1 and generate a V2 again. You can also ask it to generate those ones. And it will generate for you. Now, so for it to verify, it's supposed to verify this. I've asked it to verify. Before it verifies, it should know that V1 will be X times Y, and V2 will be Z times U. And this is our vector, our witness. Our witness will be 1 R, then X, Y, Z, then U, V1, V2. Then the left result will be L times A, then R times A, then O times, this is the output. This is the output. Now, so we now want to verify that this equals this product. We want to verify that that becomes that product. So that is what, then I ask it. Ask it, element-wise product, left result times right result. So I call this a left result times right result. I want this to be called element-wise product. And then I just want to see whether the element-wise product equals the output result, which was defined here as this. So I want to see whether, so I'm calling this element wise. You don't need to do all this. You can summarize all this into one. I just wanted to go step by step. Okay, so I think I should stop there, but when we meet next, I visit this example before we proceed to other examples, and then look at how the code then generates values. Somebody asks you, show that you know R, you are able to give this person R, suppose able to give this person all these values, all this, so that this person himself will then verify that the values you've given are correct. The values you've given are correct. Okay, thank you. I want to stop at that. That we revisit this next time when we meet.
Thank you.
Oh, I can see some chat. Somebody asked, how can I get the notes? Joanne is asking, how
Yes.
can I get the notes?
Yeah, Joanne, are you in our WhatsApp group?
Yes.
Okay. I'll share in the math group. I'll share a link to all the notes there. Also, the videos are on YouTube. So I'll share everything there.
Okay, thank you.
Okay, thank you.
Okay, thank you.